Alright, we're going to solve a problem on Cartesian force vectors in 2D, and the problem is as follows. We are given a series of forces in the Cartesian coordinate frame in 2D, and we would like to find the resultant force vector. And not only that, we would also like to find the magnitude of the resultant force vector, and eventually with the resultant force vector found out, we should be able to draw it in the Cartesian coordinate frame. Okay, so here is the problem. I have the y-axis and the x-axis as drawn. They are orthogonal to each other. Then I have a force whose magnitude is given to us as 100 newtons. This we are going to call as F1. And this makes an angle of 45 degrees with the x-axis. I have a force F2 whose magnitude is given to us as 200 newtons. And this makes an angle of 30 degrees with the y-axis here. And then I have a third force which is given to us as F3 whose magnitude is 390 newtons, and a slope triangle is given to us. The slope triangle has the following sides. It's a right angle triangle first of all. As you can see, this side is 12, the hypotenuse is given to us as 13, and this side here is 5. Now what are the things that we need to find out? Okay, so we need to find out the resultant force vector magnitude. And we want to express the resultant force vector as a Cartesian vector. And eventually we should be able to represent this resultant force vector in the Cartesian coordinate system. Right. So the key idea that we are going to employ here is the fact that the resultant force vector is the vector sum of the individual vectors. Okay, so this is the key idea. We have three individual force vectors. These are vectors F1, then I have vector F2, and then I have the vector F3. I'm going to call the resultant vector as the vector F suffix r, and so Fr is F1 plus F2 plus F3, but this is the vector sum, which means that we need to take each of these vectors F1, F2 and F3, represent them in terms of their components along the Cartesian coordinate system, and then hopefully we will be able to add up the individual components along the respective xy directions for vectors F1, F2 and F3. And another key idea here is since we are doing a Cartesian coordinate system, the component is the same as a projection. Okay, so Cartesian system, component is the same as the projection. And the idea is we're going to write each of these forces F1, F2 and F3 in terms of their I and j components, or the x and y components, and we should be able to then add up the components along the respective directions. And then once we have the components, if we can write out the vector Fr in terms of some x component and y component, where Frx is the x component of fr and fry is the y component of fr, then the magnitude is going to be the square root of the sum of the squares of the individual components here. Right. The plan here is we're going to look at each of these forces, F1, F2 and F3, and work on them individually, and then we will eventually combine them by using the idea of vector addition. Alright, so first let's take a look at vector F1. Okay, so here is vector F1. I want to write it in terms of its components along the x and the y directions. So here is the x direction and y direction, and I have the force vector F1 which is drawn here. Now this vector F1, I can break it into its components along the x and the y by drawing a line parallel to the y-axis, and by drawing a line parallel to the x-axis I'm going to get the x component and the y component. So this is the vector F1. I'm going to call the x component as F1x and the y component here is F1y. Since this is a parallelogram or a rectangle as such, then we can say that this guy is also going to be F1y. Now this is a 90-degree triangle there, and then I see that this angle is given to us as 45 degrees, which means that I can write out F1x and F1y in terms of F1 and the angle of 45 degrees here. So I see that F1x is going to be F1 cosine of 45, F1y is F1 sine 45. I know the magnitude of F1 was 100 newtons, which means this is going to be 100 times cosine 45, and this is going to be 100 times sine 45. And then we can write out the force vector F1 as a Cartesian vector by combining the components along the x and the y directions. Essentially, vector F1 now is going to be F1x in the I direction, F1y in the j direction. You notice that we are going to make use of positive I and j directions here. This is because F1x is along the positive x and F1y is along the positive y. Alright, so I have vector F1 as the following. So this is going to be 100 cosine of 45 in the I and 100 sine 45 in the j, so many newtons. And we're going to give the same treatment for the other two force vectors as well, vectors F2 and F3. Alright, so let's take a look at the force vector F2. So here is F2. We have the x and the y coordinate systems as drawn, and I have the force F2 pointing towards the origin in the following fashion, and this is the y-axis here, and this is the positive x-axis, and as we know, the positive x-axis has the unit vector I pointing this way, and the unit vector j is going to be pointing along the positive y direction. Now we perform the same operations on F2. We draw lines which are parallel to x and y axis starting in this particular fashion here, and then we see that okay, wherever these guys are intersecting, then I have the component along the y direction. This is going to be the component along the y direction, and then I'm going to have the component along the x direction. Notice how the arrows are being drawn here. So this is going to be force vector F2. This angle here is 30 degrees, which means that this is going to be F2y and this is going to be F2x. And obviously, since we have a rectangle or a parallelogram, a special case of a parallelogram is a rectangle, so I see that this guy here is also going to be F2x. And as we know, this angle is a 90-degree angle right there, and so I can write out the force vector F2 in terms of its components F2x and F2y. So first of all, F2x is going to be the following. It's going to be the angle 30 degrees and the force vector F2, so this is F2 times sine 30, and then I have F2y is going to be F2 cosine 30. F2 had a magnitude of 200 newtons, so this is going to be 200 sine 30, so many newtons, and this is going to be 200 times cosine 30, so many newtons. But the important thing is this: the force vector F2x is along the positive x direction, but you can see that F2y is pointing along the negative y direction. As a case in point, I can draw F2y here as well, and you notice that it is pointing in the negative y direction, which means that vector F2, if I write it as a Cartesian vector, this is going to be F2xi minus F2y in the j direction. And so I have F2 as the following. So this is going to be 200 sine 30 in the I minus a 200 cosine 30 in the j direction, so many newtons. And we have the last one, which is the force vector F3. We have to do pretty much the same thing. The slight difference here is that we have a slope triangle that is given to us, and we need to make use of aspects of similar triangles in order to work with the slope triangle that we have. So let's take a look at vector F3. I draw the x and the y directions. I have the positive y direction, I have the positive x direction. I'm going to extend the positive y on to the other side, and I get the negative y direction. So this is going to be positive x and this is going to be positive y, which means that the unit vector in this direction, if it is in a negative y direction, is going to be minus j, and along the positive x direction is going to be plus I, and of course along the positive y direction the unit vector is j. I have the force vector F3, which is drawn as shown here. So this is the force vector F3. Now I have to split it into its components. Before I look at any of the angle information, I have to split it into its components, and essentially here is what I do. I draw a line parallel to the y-axis, I draw a line parallel to the x-axis from the head of this force here, and I get the components along the x and the y direction. So this is going to be F3x, and this is going to be F3y. And you notice that I also have this small slope triangle which was given to us. This was 12, this was 5, and this was 13. And now we're going to make use of the idea of similar triangles. You see, I have this small triangle here shaded in red. This is going to be similar to the larger triangle that we can shade in blue, right? And just to complete the larger triangle on the bottom side, I can write this as F3x as well. And so if I just redraw these two triangles right here, I have the larger triangle, and then I have the smaller triangle. Of course these two are similar triangles. This side is 5, this is 12, and this is 13, and directions here, because we're dealing with vectors, this is F3, this is F3x, and this is F3y. And since these two are similar triangles, we need to say that the ratio of the sides are going to be the same comparing one triangle to the other. So I can say that F3x divided by F3 has to be the same as the corresponding side here, which is 12 divided by 13. And we can also say that F3y by F3 has to be the same as the side corresponding to that, which is 5 by the hypotenuse of the smaller one. Okay, so this is the idea of similar triangles that we are employing here. Once we have this ready, Then we are now in a position to write the vector f3 in terms of its components along the x and the y directions. So just to reiterate, we have f3x as essentially f3 times 12 by 13, cross multiplying from the previous page, and then I have f3y as f3 times 5 by 13, and this is going to be f3 was a magnitude of 390 newtons, and 12 and then 13 is a ratio here. This is going to be 390 times 5 by 13. 13 times 3 is 39, so this is essentially 30, and so this is going to give you 360, and that's going to give you around 30 times 5 is 150 newtons. And so we have these components, and now we want to write it as a Cartesian vector. And you notice if I go back to the previous page, if I can just bring it out again, you see that the component of f3 in the y direction is pointing in the negative y direction, component of f3 in the x direction is pointing along the positive x direction, which means that if I write them as vectors, I have the following. Vector f3 is going to be f3x in the I minus f3y in the j direction, or if I write it out in terms of whatever numbers that we have here, I have the following. f3 is essentially 390 times 12 by 13i, and 390 times 5 by 13j, so many newtons. And just to reiterate what we had for f1 and f2, I'm going to rewrite them here. f2 from before was the following. This was 200 sine 30i minus 200 cosine 30 in the j, and f1 from one of our first calculations was 100 cosine 45 in the I and 100 sine 45 in the j, so many newtons. Usually when I see cosine 45 and sine 45, I know that they are the same, so once in a while I sometimes interchange cosine and sine 45, so just watch out for that. This is not done wantonly, it's probably just muscle memory. Alright, and then the key idea is that the resultant vector is going to be the vector sum of all these three fellows, and all we have to do is perform the vector sum now. Alright, so let's do that. So I write out the resultant vector in the following form. So fr is going to be f1, which was 100 cosine 45i 100 sine 45j, plus f2, which was 200 sine 30i minus 200 cosine 30j, and then I have f3. After simplification, 390 times 12 by 13 is 360i, and then this is 150j, right? So if I add them up, if I perform the vector sum of these three, then fr is going to be the following. All I have to do is add the I components first by themselves, and then add the j components, and then I combine all of these and I get the resultant vector. So this is going to be the following: 100 cosine 45 plus 200 sine 30 plus 360. All of these are terms in the I direction, and then I have things in the j direction. I have plus sign here. I have 100 sine 45, and notice that I have a negative sign, so that's minus 200 cosine 30, and then I have a minus 150. This is in the j, and then this closes up, and further simplification of this gives me the following form. So fr is now going to be, after adding these things up, I get 530 0.7i, and then minus 252.5 j so many newtons, and this is the Cartesian form of the resultant force vector Fr. Couple of things to complete here is we need to find the magnitude of Fr, and then we also have to represent it in the Cartesian system. Both of these are fairly straightforward once you have the resultant force vector. So after the previous page calculations, we have the following. Fr is 530.7i minus 252.5 j so many newtons. It's very important that we specify the units. Without any units, these things do not make any sense at all. Then if I have to find the magnitude of Fr, all I have to do is take the square root of the sum of the squares of the components, and in this case I can interchangeably call the components as the projections and the projections as the components, because we are dealing with a Cartesian coordinate system and those guys are the same. Components are equal to projections in the Cartesian system, and so if I do this calculation here, I find out that Fr eventually is going to give me something approximately close to 588 newtons. I think the answer that I got in my calculator was 587.7 newtons, rounding it up to 588. Now I need to know how to represent this in the Cartesian coordinate system. So I draw the positive x and positive y directions. So I have positive x, positive y, this is positive y, this is positive x, and I see that I will extend the y direction in the negative side here. And so you notice from Fr, this is the x component, it's 530.7 in the positive x direction because it is a positive I. So I have this one here, which I'm going to call as Frx, which is 530.7 newtons. And then you see that the component of Fr in the y direction is minus 252.5, which means that it has to be in the negative y direction, and this is going to be Fry, which is 252.5 newtons. Do not put the negative sign here because you have already drawn it to be in the negative y direction. I'm going to complete this rectangle right here and complete this guy here as well, and starting from the pinned point of their tails all the way to the point of intersection there, if I draw this line, that's going to give me Fr. And obviously I know that since this is a rectangle, this side also has to be equal to Fry, and if I call this angle as theta r, and you see that this is an angle made in the clockwise sense with respect to the x-axis, then I can write out that tan theta r is nothing but the ratio of Fry to Frx, which means that theta r is tan inverse Fry, which is 252.5, divided by Frx, which was 530.7, or eventually theta r is going to be approximately 25.4 degrees. And the moral of the story here is that we look at the Cartesian form of Fr. From that we can write out the magnitudes here for Fr, square root of the sum of the squares, and then we also have the representation of Fr in the Cartesian coordinate system. We notice that it has a positive x component, a negative y component, and so it has to be in the fourth quadrant here. And once we do that, we can find the angle theta r made by Fr with respect to the x-axis, or if needed you can find the other angle here as well, the complementary one right there, which is 90 minus theta r. Thank you.